Hello, in this video we'll take an overview of section 5.1. We're going to take a look at double integrals over rectangular regions. We're going to first define the idea of a double integral, and we're going to define it over a rectangular region. And the idea behind here is that our partitions would be a two-dimensional partition. We can think about partitioning the x and then partitioning the y. And when we do that, we're going to split this up to a rectangular region can get split up to a bunch of little rectangles. Within those little rectangles, we're going to select some random point. Usually we're going to use a point in a corner because that's easiest, or you can use a point in the middle, but any random point would work. And you're going to take that point and evaluate it into the function, and you're going to get a height. So the area of the rectangle, a little sub-rectangle, times the height of that will give us the volume of that little box or little cube. And that's what we're interested in doing. And so we do that for one of them. We'll do it for a whole bunch along one variable. Let's say you partition your x into n different parts or m different parts. And so you're going to have an index running from 1 to m. And then you'll partition your y value into n parts, and you'll run an index called j, and then you have yourself this Riemann sum, except it's a double Riemann sum, and number of partitions goes off to infinity. Then you'll have your double integral definition. Once we do that, we'll take a look at the properties of double integrals. We're going to look at this from like a theoretical point of view. The first one says a sum and difference is implied, that the sum and difference of a double integral of a function within a double integral is the double integral of the sum and difference, or that's backwards. If we say the double integral of a sum and difference is equal to the sum and difference of the double integral, a double integral of a constant times a function is the constant times double integral. So the first two are properties that we've seen before with single integrals, and in fact they're linearity properties of the integral. The third property takes a look at splitting up your rectangular region R into S and T, and making sure that the S and T do not intersect, and so they don't overlap. Then the double integral over the big region R is going to be equal to the sum of the double integrals of the smaller of the other two regions. The fourth property tells us that if you have one function is bigger than the other function, then the integrals will be bigger if you're integrating over the same region. Number 5 tells us that if your function is bounded on top by capital M and in the bottom by little m, then the double integral will be bounded on top by capital M times the area of the rectangle, and bounded below by little m times the area of the rectangle. And then on a special case where f of xy can be seen as a product of a function of x and a function of y only, that means you can split up this function, separate the variables, so to speak. Then you can write your double integral as just integrating with respect to x as a single integral, integrating with respect to x from a to b, and integrating with respect to y from c to h, or c to d. So these are some properties. Some of them we'll use explicitly and refer back to this list, and some of them we'll just kind of know because we're naturally using it, especially like the first two. After we take a look at these properties, we're actually going to try to compute these double integrals, and the way we're going to compute them is by looking at them as an iterated integral. So an iterated integral means we're going to take the integral from the inside going out. And so the first equation, for example, talks about integrating with respect to y first, and then with respect to x, and then vice versa for the other one. For a visual of that, we can take a look at the double integral. This picture on the left side over here takes a look at the integral where we integrate with respect to x first, and we're going to get some function of y, so it's going to be an area function. And then as y changes, then that area is going to change. And so we'll take that change in area and add them all up, almost like finding the area of the volume by slicing. And then we're going to slice along the x-axis. And then we're going to find those areas. So this other example over here, we're going to take the integral with respect to x first, and then we're going to get a function of y, and then we're going to have an area as a function of y. We're going to integrate that along the y-axis. And so this is your like Fabini's theorem talks about the whole idea behind the iterated integrals. But this is going to be the basis of how we will be computing our double integrals and triple integrals when we go later on as well. And then just one simple application, or a few applications, aside from areas and volumes, there's an average value, but we could use double integrals to find areas. So imagine you have a two-dimensional region. You could probably think about using, just a single integral to be able to compute this, but you can also use double integrals. Because you can imagine if the height was equal to 1, then you're actually essentially just multiplying the area times 1. So numerically, you're going to get the area of this particular region. Now with symbols, if we take a look at that, the area is like something in square units, and then you multiply it by a third dimension, that's going to be cubic units. So the units might not match, but numerically you're still getting the same value for the area. And this is what we're going to use this a lot. The idea that your double integral, the integrand is going to be 1, will give us an idea that we're actually computing the area. We will take this idea also further and look at triple integrals to find volumes. Our second sort of application would be just the usual finding the volume between surfaces. We can find the volume over a rectangular region on the xy plane, but now we can extend that just slightly. If we have two surfaces, we can find the volume in between by using the double integral. And it's just going to be the difference of the two surfaces that goes inside of the integrand. And then finally, we have the average value function. The average value tells us that the double integral divided by the area of the rectangular region gives us the average value of the function over your rectangular region. This would be useful for things like statistics and finding the average value or the expected value of something. All right, that is a quick overview of section 5.1. All right, good luck.